Start. Now let us discuss the concept of pitot tube. Pitot tube is also a device like your orifice meter and venturi meter, and this device is used to measure the velocity of flow. It is used to measure the velocity of flow. Right, we already see that venturi meter and orifice meter are used to measure the discharge of the flow. But if you want to measure the velocity, that if in a pipe, in a closed pipe or on a river, you can say that fluid is flowing, water is flowing, then what is the velocity at some section, at some point? If we want to measure that velocity, then we can use the pitot tube. And pitot tube is based on, stagnation pressure concept. Right, we already see that what is the difference between static and stagnation pressure. So stagnation pressure is that pressure if you deaccelerate a fluid up to a zero velocity isentropically, then the pressure at that point is known as the stagnation pressure. When complete kinetic energy is converted into the pressure energy, then the total pressure is known as the stagnation pressure. Now let us see how this pitot tube is working. Suppose if I draw here, suppose in this pipe some fluid is flowing. Suppose in this pipe, let us say this is the axis of the pipe. In this pipe, let us say some fluid is flowing. Right. This is based on the stagnation pressure. Let us say in this direction, the fluid is flowing. Right. So what we can say is, let us install a piezometer here. I install a piezometer. This is the piezometer which can measure the static pressure. Right, this is the piezometer which can measure the piezometric head, or you can say static pressure. And let us say that at this point, let us say this is the axis of this piezometer. Right, this is the axis of this piezometer, and at the same point, let us say at this point we have a pitot tube. Right, L-shaped tube, which we studied when we discussed the stagnation and static pressure. That right angle tube, I installed it. That right angle tube will install here, and this right angle tube will measure the, it measures the stagnation pressure, and we will see how the things will work. Right, so this is the L-shaped tube, right angle tube, which is used to measure the stagnation pressure. And if I say that, now if I say at this point, this piezometer will read this reading. Let us say this will read this reading. It will read this reading. Let us say this is point A. Right, let us say this is point A. So this is the piezometer which can read your static pressure head, right? Static pressure head. So I can say that this reading is your PA by rho G. If you measure this, if I measure this, let us say this head is PA by rho G. This head is PA by rho G, right? And let us say that this pitot tube will measure this reading. This is the reading of this. Right, so this reading, this L-shaped will measure the stagnation pressure. This will measure the stagnation pressure at point A. This is stagnation pressure. Stagnation pressure can be written as P naught A. P naught A is the stagnation pressure head, right? So this is measure the head. This is divided by rho G. This is divided by rho G. If I take this point A, this point, one point is, these are the one point, very near point. One point is outside this section and one point is just at this section, just at the entry of this section. So we can say that this is the, you can say that this is your, at the entry of this point, and this is the stagnation pressure, that is P naught A divided by rho G. This reading is P naught A divided by rho G, and you know very well that this difference in the reading, is because of the dynamic head. We know that this difference in the reading is because of the dynamic head. So this increase in the reading in the pitot tube, right? We know that the static pressure at point A will be equal, right? The static pressure at point A will be same. But because of this pitot tube, the velocity will decrease and the pressure will increase. So the increase in the pressure, right? If you measure the static pressure at point A, it will be here only, right? Because because same fluids at the same point, the pressure will be same. So this is static pressure will be here, but it measures the stagnation pressure, and this increase in the pressure is because of the dynamic head, that is VA square by 2G. This is increased and this is equal to VA square by 2G, and this tube, this L-shaped right angled tube is known as pitot tube. This is known as pitot tube, right? So you can write, let us say this is the reading, let us say this is equal to H, right? This increase is equal to H. So I can write that H is equal to VA square upon 2G, and from here you can write VA will be equal to under root 2GH. VA will be equal to under root 2GH, right? No, you need not to be worried, right, how I write this. If you don't want to write like this, you can take 2 points, let us say A and B, right? A and B are very close, they are very adjacent to each other, so you can apply the Bernoulli between A and B. Similarly to the stagnation pressure, we say that PA by rho G, VA square by 2G plus ZA will be equal to PB by rho G plus VB square by 2G plus Z2 or ZB. These are same. VB is 0 because it is at this point velocity is 0, so you can write PB, that pressure at this point B, PB by rho G will be equal to PA by rho G plus VA square by 2G. What is the PA by rho G? This one is the PA by rho G, so the increase will be VA square by 2G, right? This total will be the pressure at point B, PB by rho G, and this increase will be equal to VA square by 2G. And we already see that this is the theoretical velocity. This is the theoretical velocity, that is under root 2GH. If I consider there is no viscosity. If there is no viscosity, but in actual viscosity is there, friction is there, and some of the kinetic energy will be converted into intermolecular energy to overcome the friction. So some of the energy will be lost, so the energy which is remain to convert it into pressure is less, so the actual velocity will be less. So to calculate the actual velocity, we have a coefficient of velocity that is written as CV. So the coefficient of velocity will be actual velocity upon theoretical velocity. Actual velocity upon theoretical velocity, and CV will be given in the question. So from here you can calculate the actual velocity, right? We know that we already defined that. What is the coefficient of discharge? Coefficient of discharge is actual discharge divided by theoretical discharge. Actual discharge divided by theoretical discharge, and this can be written as discharge is area into velocity. This is actual area into actual velocity divided by theoretical area into theoretical velocity. Right, and you know from the discussion of orifice meter, what is this actual upon theoretical area? This is coefficient of contraction. You remember that in that case, that A0 is the theoretical area which we know. This is the theoretical minimum area, but actual area is AC, or in that case you write A2. A2 is the actual area, right? A2 is the actual area. If you just take the notes of your orifice meter. So in the orifice meter we take this one. So actual area is the vena contracta area, because actually the minimum area is at the vena contracta. But theoretically, what we see by the arrangement, you can see that theoretical area is the A0, which you know, right? So this is CC, and actual velocity upon theoretical velocity is coefficient of velocity. So we can write coefficient of discharge will be equal to coefficient of contraction into coefficient of velocity. We already derived this, we already used this in the orifice meter, so here also you can use like this, right? So this is how this pitot tube will be used to measure the velocity. Sometimes in the question, right, I'm not going to solve it, but I'll explain you. Sometimes in the question, these two ends of the piezometer and this pitot tube is connected with a U-tube manometer to measure the pressure difference. To measure this pressure difference, somehow they will connect it to the piezometer. This is manometer. This will connect with one manometer, this will connect in a U-tube manometer, just like venturi meter if you remember, or an orifice meter. They will connect to a differential manometer which can measure the pressure at here and pressure at here, right? So in that case, if the manometric reading will come y is the manometric reading, right? I'm just explaining it because in some of the questions the things will be like this, that they will connect with a manometer. Suppose you understand this, I just rub this, right? I just rub this so that I'll explain it with the help of manometer also, so that you will not be confused. If it will come in the question, right? Now let us see these two ends, that is B and A. These two ends of this pitot tube and the piezometer will be connected with the, let us say it will be, I'm showing it, let us say it will be connected with a manometer, differential manometer, right? Diagram. Okay, rough diagram I'll make. Right. Let us say it is connected with a differential manometer. Here the pressure is more, so here the reading will be less. Here the reading will be more. Right. This is the manometric liquid. This is the manometric liquid rho m, and you can say here rho m is less than rho. Obviously, rho m is less than rho from this diagram. So this difference in the manometric reading, we already know this. This is, we denote it with the letter y. Okay. This is the letter y. What is this y? Y is the deflection in the manometer. But this deflection is of the density rho m. This deflection is of the fluid of density rho m. And what this y shows? This y shows the, I'm just writing PB minus PA. It is showing the PB minus PA, right? PB minus PA. But in this equation, this H is the deflection of same fluid, which is flowing. Let us say this flow is of density rho. So this H is of that same fluid which is flowing. But here the fluid is changed. So we know that how to convert this y into H. So you know that the same procedure, H will be equal to y into, in this case it will be rho m by rho. So you have to put in this equation H will be equal to y into 1 minus rho m by rho, because H here is of density rho. But if manometer is connected and there is a manometric fluid, so it is this y is of density rho m. You have to convert it, right? I already show you in the venturimeter how to convert it. So I'm just using the result of the venturimeter. The same result will come here, right? Because PB minus PA upon rho g will be equal to VA square by 2g. You know this, right? So this y is a function of velocity only, because it shows the dynamic head only. But the problem is that here the density is rho m, but we want the H of density is rho. So how to convert it? With the help of this formula. And if rho m is greater than rho, then you know that H will be equal to y into 1 rho m by rho minus 1. You know this, right? The same thing will be applied here also. The same derivation, same formula will be applied here also. So this is all about pitot tube, which is used to measure the velocity of the flow, right? So in the aeroplane, if you want to measure the velocity of ship, velocity of river, or in any pipeline, if the petrol, diesel is flowing, so if you want to measure by which velocity they are flowing, so if you want to measure the velocity, then this pitot tube is used, and it is based on the stagnation pressure. You have to remember this, right? Stop. Start. Now let us discuss the time of emptying a tank, right? We have a tank. Let us say that there are two cases of this topic. One is when the tank is of uniform cross-sectional area, and another one is the tank when it is of non-uniform cross-sectional area. Now let us first discuss about the uniform cross-sectional area tank. Suppose this is a tank. It is filled with some fluid, some liquid. It is filled with some liquid. And this tank is of uniform area. The area at each and every section on this tank is uniform, and let us say that capital A is the area of this tank. And initially the water level is at height h1. The water, I am saying water, or the liquid level you can say. Initially the liquid level is at height h1, right? There is a small orifice at the base of the tank, and area of this orifice is small a. And from this orifice the liquid will start coming out, and this height will start decreasing, and after some time this height will zero and completely tank will be evacuated, tank will be empty after some time. We need to find what is the time required for this tank to be empty. We need to find out this. Now we can say that at this orifice the fluid is coming. Let us say the fluid is coming with velocity, let us say v, and that v will be equal to under root 2gh. We know this, that v will be equal to under root 2gh. How we will get this? You can apply your Bernoulli equation between this free surface and at this exit of this orifice. If you apply the Bernoulli equation, then here the pressure is atmospheric, here the pressure is atmospheric. So that pressure terms will cancel out. Here the velocity of the fluid is 0. So at point A only z will be there, and if you take this datum, then z here will be equal to h1 is equal to v square by 2g plus z2. Z2 here will be 0, so v will be under root 2g h1 at this time. So we can say that the velocity at this point will be equal to the under root 2g h, where this h is the height above this orifice. And you can see that as the time goes, this height will decreasing, right? As the time goes, this height will decreasing, so this velocity will decrease with time. This velocity will decrease with time because this height is decreasing. So if we want to find out the time required to empty the tank, right? If this velocity is not decreasing, we can easily say. But if this velocity is decreasing continuously, so we cannot say how much time directly. We cannot say how much time is required to empty this tank. Now, like this problem can be solved. This type of problems can be solved with the help of integration. We know this, how to solve this type of a problem. So I am saying, let us say that at any time t, let us say at any time t, the level in this tank will be this one. Let us say that at any time t, the level in the tank is this one, and this level, this is, let us say, at a height small h. This is at some height small h. At any time t, I write at any time t. And we can say that for some infinite small time dt, this height will decrease from here to here. Water will flow and this height will decrease. This height will decrease in time small time dt. We can say that this height will decrease to, let us say, dh. Right. So I can write dh is the height of liquid level decrease in time dt, very small time dt. Right. So if I apply the continuity equation, or you can say conservation equation, right, I can say that the volume of the liquid displaced in the tank, how much is the volume decreased? This is the area into height. This much amount of volume water is decreased in the tank, and this volume will flow through this orifice, right? There is no other way for this water to go, right? So the decrease in the level of the water, the decrease in the volume of the level, I can say that the decrease in the volume in the tank will be equal to the volume flow rate through the orifice, right? It will be equal to the volume flow rate through the orifice. So if I apply the continuity equation says that the volume of water decreased in the tank will be equal to the volume flow rate through orifice, volume flow rate through orifice into time, because units will be same. Here I take volume, so here the unit will be volume only. So how much is the volume decreased in the tank? The volume will be area into how much is the height decreased, dh. This is the volume of the water decreased in the tank for time dt. What is the volume flow rate? Volume flow rate is discharge. Discharge is area into velocity, right? Into coefficient of discharge if it is not an ideal fluid. So the discharge will become here is CD, coefficient of discharge for some velocity, viscosity, some viscosity is there. So coefficient of discharge into area of this orifice is small a, into velocity will be under root 2g into small h. At this time the velocity is your under root 2gh. We are neglecting the dh with respect to h, right? Into time is how much? dt, right? Time is how much? dt. So this is a continuity equation. Now it is very simple to solve it, right? We reach to this equation. Now it is very simple to solve it. I can write it like this: capital A by small a into 1 by CD into dh divided by under root 2gh is equal to dt. Right? This equation we got. So we can say that this is the equation. So we can say if we want to find what is the total time required to empty the tank, so we have to integrate it. When time is zero, what is the height of the level of the liquid level in the tank is h1. When the time is zero, then the height will be h1. And if we want to empty it, then at time t, let us say at time t is the time at which the liquid level will become zero. So what is the height now? Zero. What is the height now is zero, right? So if I integrate it, you know this is constant, that can be written now, right? CD into small a. This is under root 2g into this is integration of h raised to power minus 1 by 2 from h1 to 0. This will be equal to dt integration is t, so this is t minus 0, so t. So this can be equal to a divided by CD into a into under root 2g. What is the integration of h raised to power minus 1 by 2? H raised to power minus 1 by 2 integration is h raised to power minus 1 by 2 plus 1 divided by 1 by 2 minus 1 by 2 plus 1. Right? This will be the integration. So this will be equal to h raised to power 1 by 2 divided by 1 by 2. This is 2h raised to power 1 by 2. Right? 2h raised to power 1 by 2. So this will be 2h raised to power 1 by 2 will be equal to, from limit h1 to 0 will be equal to t. One mistake we did, there is a minus sign here. Now why minus sign? Because with the time this height is decreasing, right? This minus sign is because with the time height is decreasing. With the time height is decreasing, so we have to take the minus sign, right? dt and dh, if we take the reference, so we have to take the minus sign. This mistake we did, okay. So if I put the limits, then time t will be equal to under root 2 into a into capital H1 under root H1 divided by CD into a into under root 2g. Right, this will be the time required to empty this tank. This will be the time required to empty this tank. I put the limit, first I put the limit 0, then this will be 0 minus H1 if I put, so minus minus plus, so it will be under root 2 will cancel, so under root 2 a under root h divided by CD into a into under root g. So this will be the time required to empty this tank. And if they ask what is the time required to come to height h2, let us say there is some height h2, right? If they want that, what is the time required, what is the time in which this level will come from h1 to h2, so you have to take h1 to h2, right? Then you can do the integration. There is no big thing here, so you can do the integration here, but I want from h1 to 0, so I take the limit 0. If you want to take from h1 to h2, then you can do like that only. So this is how you can do the problem for uniform cross-sectional area and you want to empty this tank. Stop. Start. Now let us see what is the time taken to empty a tank, and now we will discuss the second case, that is when the tank area is non-uniform. Earlier we discussed the uniform area of the tank and the time taken to empty that tank of uniform area. So when we integrate that equation, continuity equation, when we integrate, we take the area as a constant and we integrate it. Now if I can say that, let us say this is a hemispherical ball in which fluid is there. This is the initial level of the fluid, that is at height h1 from the base. So as we go down at each and every section of this tank, area is decreasing, right? Area is decreasing along with the height, area is decreasing. So now if we want to integrate it, we can't integrate by taking the area as a constant. So we need to find the relationship between the area and this height, right? We need to find out some relationship. We need to find. Now let us see how to solve this kind of equation. We can say that if let us say capital R is the radius of this hemisphere and initial level is capital H1, we have a orifice at the bottom of area small a, same terminology we are using, and from here water or the liquid is coming out with some velocity v. So I am saying, let us say after some time, let the liquid level will be at a height capital H, and in time small time dt, the level will fall down, that is dh. The level fall down is dh. So if I apply the continuity equation in this case, the continuity equation will be the volume which is decreased in the tank, the volume of the liquid which is decreased in the tank is equal to the volume flow rate from this orifice. So I can write that how much volume decreased is minus sign because height is decreasing with the time. So minus of a of this cross section, let us say this section is xx, let us say this strip is xx, so area of this strip xx into height, that is dh, will be equal to volume flow rate is your area into velocity. So CD into area is small a into velocity is under root 2gh into time dt. Same equation we know, the same equation I write here, but now I can say that, okay, no need to mention a into dh. Now this axx is not constant. Now this is not constant, so we have to find what is the value of this axx. So if we find out from this, then axx will be equal to, this is a circle, right? This is a circular section, so this will be equal to pi x square. Let us say this radius, the radius of this very small thin section is x, so the area will be pi x square. Now what is the value of x? So if you want to find out the value of x, so I can say that this x will be equal to, if you see from here, this is capital R, right? If this is the center, I can say this is the center, right? So okay, this is not R, right? If this is the center, this is the center of the hemisphere, so I can say that this value is capital R, this distance is capital R, right? Now this is capital R, this is h, so this remaining height will be capital R minus h, and if I join with this like this, if I join this, then this distance is capital R, radius obviously. So if I apply a right angle triangle Pythagoras theorem here, so I can write hypotenuse square, that is capital R square will be equal to this line square r minus h square plus x square. We need to find the value, the function of x in terms of r or h, we need to find out. So I can write like this Pythagoras theorem, so it will be r square minus h square plus 2rh will be equal to x square. So from here you can write x square will be equal to 2rh minus h square. X square can be written as 2rh minus h square, right? So from here this equation will become, instead of axx, I can write from here, I can write minus pi x square. X square is 2rh minus h square. This is into dh is equal to cd into a into under root 2gh into dt. So if I take this, right, so from here you can write dt will be equal to minus pi into 2rh minus h square into dh divided by under root 2gh. Now we want to integrate it. If the time is 0, then the height is h1. If the, let us say, time is t, then the height is 0 to empty the tank. We want to find out the time when this complete fluid is out of this tank, when the tank is empty. So you take the height in the final will be 0. So if you solve it, right, this is a very simple integration, you can solve it. I am just writing the answer. Then in this case, the time will be, no need to remember this, just you can check by solving this integration. This will be 14 pi into r raised to power 5 by 2 divided by 15 cd into a into under root 2g, right? So this will be the case. So this is the thing when, and okay, and initially this you can see that this h1 is equal to r, right? This h1 is equal to r, right? I take it up to the top level, so this h1 is equal to r. So I put h1 is equal to r here and I solved it. Then the time taken to empty this tank will be this one, right? And if in the question, if they can say from h1 to height h2, so you can take limit here h2, then you can see that from h1 to h2 height, when it comes to h2 height, how much time it will take. So you can solve for this. So this is a way you can solve for the time taken to empty a tank when the cross section is not uniform. In the question, if in exam, if question comes, they can give you a parabola, any other shape they can give. So they can give you a relationship between radius and some coordinates. Like if it is a parabola, and they can give like x square is equal to 4ay, or some parabolic relation they can give between radius and your x coordinate. So you can easily find out the function of area in terms of h, right? And you can put this in this integration, in this equation you must remember. So in this equation you can put, then you will get the answer. So this is the way you can solve the question. In the GATE, very less chances there that their question will come on this topic, but in the engineering services they may ask a subjective type of question from the tank problems, right? Stop. Start. Now let us discuss a very important concept or very interesting concept in the fluid mechanics, that is the principle of a hydraulic siphon, right? Siphon is just basically a pipe or a tube which is used to carry the fluid from one point to another point. We will see its practical application also, but first of all let us understand how a hydraulic siphon will work. As we know from the Bernoulli equation, we can say that the fluid will flow from high energy to the low energy, and where energy means the sum of pressure energy plus potential energy plus kinetic energy. So the fluid is, if you remember your school days or 11th 12th class, you are saying that fluid is flowing from high pressure to low pressure. No, it is not true. Fluid is not flowing from high pressure to low pressure. Fluid is flowing from high energy to the low energy, right? Where the sum of these three, pressure plus kinetic plus potential energies, are more, then the fluid will flow from these total mechanical energy, from high total mechanical energy to the low total mechanical energy, right? And this is the basic principle of your siphon. So we will see the practical application of siphon later on. Let us discuss that. This is a tank. This is a tank in which some fluid is filled, and I want to empty this tank, right? I want to empty this tank, and I don't want to use a pump, or I don't want to make an orifice in this, right? We can say that we can empty this tank. If we make an orifice here, then tank will automatically empty, or we can use a pump to empty this tank, but we don't want to use the pump, or we don't want to make an orifice. So to empty this tank, we can use this kind of a pipe. This is a normal pipe, siphon. This pipe is known as siphon. And we are assuming that this cross-sectional area of this pipe is uniform. The cross-sectional area of this pipe is uniform, and one end of this pipe is dipped in this tank, and other end is set to the free to the atmosphere. Just one thing you have to take care that the end of this second end of this pipe will be below the level of the liquid in the tank, right? We will discuss it why. So if this is the case, and I am saying that, let us say this is the initial level of the tank, and I mark some point, let us say this, at the free surface I take a point A, and at the exit here I take a point B, right? So if I apply the Bernoulli equation between point A and B, right? If I apply the Bernoulli equation between, just pay attention guys, we will get a very good interesting result how a siphon will work. If I apply the Bernoulli equation between point A and point B, right, I'll write it. The equation will be look like this: PA by rho G plus VA square by 2G plus ZA, elevation of from some datum, is equal to PB by rho G plus VB square by 2G plus ZB, right? And by writing this, I am neglecting the losses. I am not considering the losses, right? Neglecting losses means I am not considering any viscosity, any friction which is present. I am neglecting it. So this is the Bernoulli equation between point A and point B. So I can say that, we can say that at point B pressure is atmospheric, at point B pressure is atmospheric, and at point A also the pressure is atmospheric. Here the pressure is atmospheric. Velocity at point A can be neglected, right? Because here the area is more with respect to the point B, right? Sorry. Here the area is less, so the velocity is more. If you apply the continuity equation between here and here, so the velocity at point A can be neglected with respect to velocity at point B, because here the area is less, so the velocity is more. Here the area is more, so the velocity is very less. So I can neglect it. So from here I can write this equation. This will become, this PA, PB will cancel out, BA will become 0. So from here I can write VB square by 2G is equal to ZA minus ZB. ZA minus ZB, and the difference between these two elevation I termed is at, let us say, delta Z. I take it as delta Z. So from here I can get that velocity at point B will be equal to under root of 2G into delta Z. Velocity at point B will be equal to under root of 2G delta Z. So from here I can say that the velocity at point B is created, right? Initially this velocity is not there. This velocity is created at the expense of difference in the potential head of point A and point B, right? Why I say that this level will be below the tank level? Because if suppose you take this at this, suppose for example, just for your understanding, if I keep this tube, this siphon up to here, let us say at this level, right, at this level. So when the tank is emptying, when it reach here, then the difference between A and B is 0. Velocity is 0. Then the tank will stop here only. Here itself. Tank will stop here itself. Right. This amount of liquid will not be fall down. Right. This siphon will not be able to take this much amount of water. So this end will be below the tank level, so that complete tank can be evacuated. Right. This is the basic concept. From this equation you can see if delta Z between this surface and this end will be 0, then we can say that Vp will be 0, fluid will stop. Velocity is 0, then the fluid will stop. Right. So we can say that velocity at point B will be created at the expense of difference of the potential head of point A and point B. And this justifies the flow from this tank through this pipe, because this delta Z here is positive, so this Vb is positive, so fluid will start flowing automatically. What is the beauty of this is that fluid will start flowing automatically. You don't need any pump, you are not creating any orifice, you just put a pipe and make this second end will be below the tank level, fluid will start flowing automatically, right? No pump, no external work is required. So this is the beauty of this siphon. So siphon is used to transfer the fluid from one container to the other container if there is a difference in their elevation. That is important. The difference must be there between their elevation. That difference must be there. If that difference is not there, if they are parallel, then the fluid cannot be transferred. Up to a certain limit, okay, you can transfer, but not so much, right? So this is the case. So siphon can be used to transfer the liquid from one tank to another tank, one reservoir to another reservoir, without taking the help of pump, right? We are not installing any pump here, right? So I can say that, let us say if you take the viscosity, right? If the effect of viscosity can be considered, let us say the effect of viscosity is considered. Then what is the equation of Bernoulli equation between point A and point B? It will be PA by rho G plus VA square by 2G plus, you know this, I'll write fast, ZA will be equal to PB by rho G plus VB square by 2G plus ZB plus head loss. So if you solve it, similarly PA is equal to PB, VA is equal to 0, you can neglect it. So from here you can get that VB will be equal to under root 2G into delta Z minus head loss. Right, if you consider the head loss, 2G into delta Z minus head loss under root, right? And we can say that here this HL is the loss of total head due to the fluid friction, and if the flow is from point A to point B, this is the total head loss. So because of this, the velocity will decrease, VB will decrease. Here in this case, the VB is less than this VB, right? So we can say that. So we can say that now this is how you can justify that, yeah, siphon is working without the help of any pump or any external work. Now, one more important concept I want to share here. Now let us apply a Bernoulli equation between point A and C. Let us apply Bernoulli equation between A and C. Right, and we are considering the friction effect itself. Let us say this difference between A and C, this height difference is, let us say, small h, right? So if I write the equation, then it will be PA by rho G plus VA square by 2G plus ZA is equal to PC by rho G plus VC square by 2G plus ZC plus head loss. Head loss we are considering. Now, important thing, please pay attention. PA is how much? PATM. VA is 0. I can write VC will be equal to VB. This VC, here the velocity will be equal to the velocity here if the area of this pipe is uniform. From the continuity you can say if the area is uniform, then the velocity is uniform. This you can write if your area is uniform. And I am considering the uniform area. For your understanding, I am considering the uniform area. So from here I can write, if I put all these value, then I can write that PC by rho G, just pay attention guys, PC by rho G will be equal to, here we have PA is PATM by rho G minus VC is VB square by 2G, minus head loss, and ZA minus ZC. ZA minus ZC will be H minus H. This will be PC, right? This will be PC. So therefore we can see that from this equation, this is, you can write here, this will be equal to PATM upon rho G minus of, I take this common, VB square by 2G plus H plus head loss. If you confuse this, that this head loss and this head loss is equal, okay, I'll take head loss dash. This is flow between A and C only, not from the whole pipe. So you can see that from here that the pressure at point C, pressure at this point C is less than the atmospheric pressure. This is the important concept which I want to say. Here the pressure at point C is less than the atmospheric pressure, right? And this implies physically that a part of pressure which is available at point A, right? At point A pressure is available, right? That is atmospheric. And now when the fluid will reach to C, this pressure comes down, this pressure decrease. So the sum of the energy of the pressure is converted into some other energy. So we can say that the pressure head at A is responsible for the gain in velocity. Velocity is increased at point C. If I neglect the velocity at point A, then at point C velocity is increased, that is equal to VB. So this increase in the velocity, this increase in the kinetic energy, this energy must come from somewhere, that is from the pressure energy. So we can say that this can be, this is responsible for the gain in velocity and the potential head, right? Your potential energy is also increasing, head is increasing. So potential head of the fluid at point C, and this pressure energy will also used to overcome the friction between point A and C, that is this HL dash, right? So this pressure energy which is available here is converted into some of its kinetic energy into its potential energy. Potential energy is also increasing at point A, potential head is less, at point C potential head is more, so potential head is increasing. So it is responsible for the gain in this potential head, plus this pressure energy is also overcome the friction between A and C. It is also overcome the friction between point A and C, right? So because we can say that, now we can say that the minimum pressure in the flow, right? So we can say that if the fluid is flowing in this direction, in the upward direction, the pressure is decreasing, the pressure is continuously decreasing, right? So where the pressure is minimum, then the pressure is minimum at this top point. Then the pressure is minimum at this top point. As the fluid is flowing in this direction, it has to increase its potential head more. So it has to, if the fluid is flowing from point A to point D, I can say if point A to point D it is flowing, then it has to increase this much amount of potential energy. It has to overcome the friction from point A to point D. So more pressure will convert into these energies. So the pressure at point D will be minimum, right? At point D, the pressure will be minimum. So if I write if I write the Bernoulli equation, if you see that what is the pressure at point D. If you write the Bernoulli equation, then the pressure at point D will be equal to PD by rho G is equal to P ATM by rho G minus velocity is same. I take velocity as same because of uniform area plus, now this difference is capital H, right? This difference is capital H plus HL, let us say double dash. This is HL double dash is from point A to point D. So you can see that this will be the PD, right? This will be the PD, and you know that if you neglect this HL double dash, then VB square by 2G. From here you can write VB square by 2G is delta H, so this will be delta Z. So this will be delta Z plus H plus HL dash, HL double dash, you can see. Now, what is the problem here is that this is the minimum pressure, you know, this is the minimum pressure. From here the pressure will not decrease. This is the minimum pressure, and this pressure is less than atmospheric pressure. This pressure is less than atmospheric pressure by this value, and if you increase the height, if you increase this distance, this height, if you increase so much that the pressure at point D will reach to the vapor pressure of this liquid at this temperature, then water will start boiling, right? Because this PD is a function of this H. This PD is a function of this H. If you increase the H so much that if this PD will be reached to the level less than or equal to the vapor pressure at this temperature, then the water will start boiling. Water will start boiling. So when water will come here, it will convert into vapor. It will convert into vapor, right? Then the whole function of siphon will be not useful, right? You apply this siphon to transfer the water from here to here, but now the height is so much that here the vapor will form. Water will start boiling, vapor will start flowing, and you know that when the vapor will start flowing and when these vapors will go to the high pressure region, they will burst a high pressure wave generated, and it causes the cavitation. It causes the cavitation, and this we don't want. So you have to, there is a restriction on this capital H. There is a restriction on this capital H, also on this, but it is very less. So there is a restriction on this capital H, that this capital H cannot exceed up to a limit, so that there should not be a vapor pressure condition is there and cavitation will occur, so it will be not useful. So if we talk about water, for water if we talk about this height will be 2 meter. For water this will be 2 meter. So you cannot increase the height, this H, beyond 2 meter for water, right? The difference between this and this will not exceed to 2 meter for water, otherwise water vapor will start forming, right? So this is the limitation for this, otherwise the siphon will work if you take care of this limitation, and the siphon will work. Now if you see about the practical application of siphon, right, in the home also, in your childhood, when you want to empty any tank or anything, right, so you just take a pipe, you suck it so that it can fill with that water, that petrol, that lube oil, anything. You suck it very slightly, you suck at one end, dip it on the other end, you suck it, and you just put it in the ground below the level of this, and you can check it at your home also. You can check this experiment. Take a bucket, right, and take a very small pipe of uniform dia or any pipe you can take and suck it. Or you can do like this, you take a pipe, fill it with water, take a bucket full of water, immerse one end of the tube in the water in that bucket and other end in the open to the atmosphere, so that the level will be not up to the tank or bucket, level will be below, then water will start flowing continuously. One thing most important, please take care, there should not be any air trap in this, right? If air is trapped, then it will be difficult for you. There are clauses like that, there should not be any air trap in that. That's why we suck it, so that it will be completely filled with that water. So instead of sucking it, so you can do that, you can fill the tube with water, and then water will start coming. So in the childhood you will do so much experiment, right, in the summer seasons, right? For if you have some memories, then you will if you want to empty your cooler, desert cooler, then you can use this technique, right? And if your bike, right, in some of old days, if you remember that when you ride a scooter, so in the scooter or bike, when petrol will be less, right, if the petrol of some other bike you want to transfer it from one bike to another bike, you do this experiment, you are doing this experiment, that experiment is known as siphon only, right? And this is how this siphon will work. Stop. Start. Now in this session we will discuss the concept of the vortex flow, right? This is also a application, this is also a topic, you can say, in the fluid dynamics, right? Vortex flow is that flow of a fluid, if that flow of a fluid is along the curved path, if the fluid is flowing along a curved path, or you can say the flow of a rotating mass of the fluid is known as vortex flow, right? we can say that if the fluid is flowing in the rotation, in the circular form, in the curved path, if the fluid is flowing, then that flow is known as vortex flow, right? So there are two types of the vortex flow. The first one is the forced vortex and second one is the free vortex. Forced vortex is that flow in which some external torque is required to rotate the fluid, right? Suppose you have a container, suppose we can say, let us say that we have this container. Let us say you have this container which has some liquid in it, let us say this is the liquid present in it, right? At present this container is at rest. So if you provide a torque, or you can say if you provide a rotation, this is a shaft, and if you provide a angular velocity to this tank, if you rotate this tank, then this fluid inside it will also rotate. So that is known as forced vortex. And after the rotation, if I draw here, the fluid free surface will be like this. This is the container, it is rotating with some angular velocity omega. This angular velocity omega you are giving to from the external to it. So the fluid free surface will be like this. The fluid free surface will be like this, right? Here the fluid is, here we have the fluid. So the fluid surface will transform from this shape, this straight line, to this curve shape. This is a parabolic shape, right? So this type of the vortex is known as forced vortex when you are giving a torque external to the system, right? And we can say that if you are giving some angular velocity omega, from the outside, then that container rotates at a constant angular velocity omega. This angular velocity omega will be constant if you are giving it from the outside. So we maintain this angular velocity as the constant. And if you want to find out what is the tangential velocity, of a fluid particle, suppose if you rotate this, let us say that I am saying this is the axis of rotation, right? We are saying that, let us say this is the axis of rotation. So if you want, this is rotating with an angular velocity omega. If you want to find out what is the tangential velocity of a fluid particle, in this case, suppose we want to find what is the tangential velocity of this, and you know that if any body is in rotation, then the tangential velocity will be given by this relation, that is V is equal to R omega, right? Where omega is this angular velocity and R is this radius of rotation. Radius of rotation of this particle. So the tangential velocity of this particle will be equal to R into omega, right? Similarly, you can calculate the tangential velocity at each and every point. So the tangential velocity at this point will be 0, and as you go in this direction, the tangential velocity will increase, right? So this is equal to R omega. So if I can write that in this case, omega will be equal to V by R, and that is constant. We maintain this omega as a constant. So the fundamental relation for the forced vortex is V by R is constant. We have to maintain this V by R as a constant. And if we can say what is the example of the forced vortex is, right, if you rotate any fluid by applying a external torque. For example, if we see the practical example, if I can say, then the practical example, first example, you can take the example of washing machine, right? In the washing machine, we are giving the external torque, right? We are giving some electric energy and that motor is rotating, and because of that rotation, the water inside that washing machine is rotating. So that is a case of forced vortex. Another example, if I say, suppose you have a fan, right? Fan is there. In that fan, when the fan is switched off, so at everywhere air is there. Air is also a fluid. So when this fan will start rotating, the air which is in contact with this fan, then it also starts rotating. That is also a kind of forced vortex. And if engineering practical applications, if we want to see, then flow inside the impeller of a pump, right? You will learn this, what is the impeller, what is the runner. Just now, flow in the impeller in that blades are there, that blades are rotating with the help of some motor, right? So the flow in the impeller is a forced vortex, and flow through the runner of a turbine, right? When the fluid strikes the runner blades, they will start rotating, right? Then that rotation of the fluid is known as forced vortex in case of runner only, right? So this is all about the forced vortex. We will list some equations for the forced vortex in our later discussions. Second type of vortex flow is known as free vortex flow. In that free vortex flow, no external torque is required. We are not giving any external torque, right? It may be the case, suppose if I say you that if there is a fan, right, I just push the fan, I just give some angular velocity to the fan, and I remove this angular velocity, then the fan will start rotating, right? Now in that case, when there is no external torque and fan is rotating, and on that fan the air which is in contact with that is also rotating, that is a free vortex, right? You can convert that forced vortex into free vortex. Suppose the fan is rotating, you just switch off the fan. Now the fan is rotating because of its momentum only. We are not giving now any other external torque. That fan is rotating because of its momentum. And in that case, the fluid which is rotating because of that fan is under the free vortex, not forced vortex, right? This is the example. This is how you can transfer, you can convert forced vortex into free vortex. You can relate it that if the external torque is continuously, you are giving external torque and the fluid is rotating, that is forced vortex. And if there is no external torque is there and still the fluid is rotating, then it is known as free vortex flow, right? So this is the basic difference between it. So if we see the example will be the flow in the casing. In the casing, we have two flow. One is the first of all, the fluid is flowing through the casing, then from casing it goes to the impeller of the centrifugal pump. So in the casing we have guide vanes, but those guide vanes are fixed, they are not rotating. So in the casing the fluid is rotating on its own, that is a case of free vortex. Second one is the whirlpool. In the river, whirlpool is there, right? Because of, you can say cyclone is a case of your free vortex. Whirlpool which is in the river, which is produced in the river, that is also a kind of free vortex. Another one is the flow of a liquid through a hole provided at the bottom of the container. If this is a container, and I provided a hole here, then the fluid will come down from this hole while rotating. So that is known as your free vortex. This is an example of your wash basin, that you are using wash basin at your home. So this is that example, and if you see, if you want to analyze, if you want to visualize the free vortex, you just put the hand at this outlet and completely fill the washing. That wash basin you completely fill, and if you remove this, if you remove your hand, then you can observe that fluid will start flowing while rotating. Fluid will start rotating and then coming out of this outlet. So that is a case of free vortex. No external torque is required. So if we want to analyze, if we want to give the equation for it, so we can say if there is no external torque, then the torque will be equal to 0. And from the Newton's law, you know that torque will be equal to the rate of change of angular momentum. So we can say that the rate of change of angular momentum will be equal to 0. So we know that what is the angular momentum? You know very well, the angular momentum is equal to mass of the fluid or mass of the body into linear velocity into radius of rotation. So that angular rate of change of angular momentum means that d by dt of angular momentum dvr will be equal to 0. So that means this mvr will be constant. mvr will be some constant. So we can say that for a given mass, if the mass is constant, mass remains constant, then we can say velocity into radius is constant for free vortex. For free vortex, velocity into radius of rotation will remain constant. But in case of forced vortex, v by r is constant, but here v into r is constant. So these are the basic equations of the free vortex and forced vortex. Now we will see what are your equation governing this vortex flow. We will discuss it in our next session. Stop.